So, that's the method of gradient systems. Now we can move on to Krasovskii's theorem, which is another theorem, and it looks quite strange as well, but in some sense it's quite straightforward, right? So what is Krasovskii's theorem? It says something like this. If you take the partial of f with respect to x, which is a function of function, but it's a matrix function. If it satisfies this particular condition, A transpose P plus P times, sorry, not A, this partial f with respect to x transpose P plus P times the partial f with respect to x, if that happens to be less than or equal to minus x for all non-zero x, actually for including x equals 0 is also fine. If sorry, that won't be, no, it should be true only for non-zero x, then we can say something, right? Please note that this inequality is not on constant matrices, but actually functions of matrices. So in that sense, for every x, one has to check this particular matrix inequality for the sense of positive definiteness. So by the way, how does one check positive definiteness of a matrix? The definition itself is basically a symmetric matrix M is positive definite if x transpose mx is positive for all non-zero x. That's the definition that I like, and one can show through diagonalization and things like that. That's equivalent to saying that all the eigenvalues of M are positive, right? So there is no set method therefore to find out whether matrix is positive definite or not. We can use eigenvalues or simply check this x transpose mx type of thing. So not that easy, right? So this is going to be a method that is quite interesting for small systems, 2x2 systems and things like that. But for anything bigger, then finding whether some positivity is satisfied or not is not going to be easy anyway. But if we can find somehow satisfy this particular condition, then the conclusion is quite straightforward. This zero solution is asymptotically stable. One can even guarantee global asymptotic stability actually. So, and it turns out, the way this works is basically the Lyapunov function is f transpose px, okay? And if it's all satisfied, actually, there are many nice things about this particular result is basically it doesn't happen without having one isolated equilibrium point at 0. You cannot have Lyapunov stability kind of a thing. You will have a asymptotic stability and then radial unbounded condition. All those things will be satisfied automatically, right, if you satisfy these conditions. So we get global asymptotic stability if this condition is satisfied at all Rn. If it satisfies around a region, then we'll have local asymptotic stability. But if it satisfies, we don't need additional radial unbounded condition and things like that. So it's a, I mean, I'm not going to prove this particular result. I'm not going to convince this particular result how it is derived, but one can actually use this Lyapunov function and go use these conditions and then show if you're familiar with linear algebra, it's relatively straightforward, right? So that's Krasovskii theorem. That's one way of finding Lyapunov functions. Okay. So the nice thing about it is, again, it uses the power of f. In the previous gradient systems, basically we use this f, try to find some complementary function g, that satisfies certain things, and then use that g, integrate and get v. Whereas in this particular case, Krasovskii theorem is more direct, and then you can write your Lyapunov function directly in terms of f. But f has to satisfy a very restrictive condition like this condition. You have this f prime transpose p plus p f prime is less than or equal to minus r for some positive definite r, right? So to demonstrate it, we will look at an example. So again, if you actually take this particular example and linearize it, you will have this Jacobian matrix minus 3, 1, minus 1, and the trace of A happens to be minus 4, and determinant of A is 2. Therefore, 0 is locally exponentially stable, right? We get local results in both the examples that we chose. But if we want global result, what can we do, right? That's the question we have. So if we actually compute this partial of f with respect to x, then we end up with this interesting matrix, and by simply adding itself to its transpose, it is a symmetry matrix, but I'm just applying the theorem the way it is. So if we add it, basically we'll end up with this function, which we can easily show that's less than or equal to minus this matrix, and the matrix on the right hand side, 6 minus 2 minus 2 2, happens to be positive definite. How do I know? The trace is 8 and the determinant is trace is 8. Yeah, the determinant is 6 times 2 is 12. 12 minus 4 is 8, right? So both trace and determinant are 8, and that's enough. I mean, if you have a symmetric matrix, checking positive definiteness for 2 by 2 systems, you know, if you check both trace and determinant as positive, then that's enough, right? For higher dimensional, like 3-dimensional and things like that, those become necessary conditions. You know, trace has to be positive, determinant has to be positive, but it's not sufficient to prove that it's positive definite. But luckily for 2-dimensional systems, that's enough. So we have this condition: something times identity, I don't write the identity here, plus identity times something is less than or equal to minus some positive definite matrix. So this becomes your R, and P becomes your identity, and therefore Krasovskii condition is satisfied with P equals identity and R is equal to this, and we end up with Lyapunov function V of x is equal to F transpose P. P is identity times F, and then we can show that that ends up being this sum of squares. So it's not surprising that all of these things eventually will produce sum of squares, and I'm trying to convince you that basically you know, a lot of these examples can be actually solved using the more general method sum of squares. But you know, for many simple methods, we may not have to resort to MATLAB or something to actually compute some of these things. So we can actually do these simple checks. So the next method is basically called Zubov's method. I'm not going to really go through an example or details in this particular case, but essentially it's another set of conditions, but stranger than everything else. Basically, you're looking for some V on a bounded set D, and this V is going to, you know, go to reach 1 on the boundary of this thing, and then we have another strange function h of x, which is also similar to V, that satisfies these conditions here. And if that happens, then basically we can show that this zero solution is asymptotically stable with region of attraction D. And you know, it's one more result, and then there are other results called energy Kashmir methods and things like that. All of them are restrictive. In all these cases, we can actually find examples where these are applicable, but you know, it's not necessary that they're very easy to implement. But it's good to know. Like I said, you know, finding Lyapunov function remains enough, so knowing as many results as possible is useful. Okay, and so that leads us to the very interesting idea. So what are the two conditions that we have? V of x being positive definite, so that is V of x is positive for all non-zero x, and V prime of x times f of x, another function of x, has to be again negative definite, you know, less than 0 for all x non-zero. So one simple thing, the idea of sum of squares is basically you can guarantee at least non-negativity, okay, if somehow V of x is sum of squares. We have seen earlier, basically V of if it is summation of half x1 square plus half x2 square, it's automatically positive definite. If it is half x1 square plus half of x1 plus x2 whole square, then it's also positive definite. Certain cases, you know, if you pathological cases where we can find that you have a bunch of sum of squares, but we may only have non-negativity but not positivity. You know, let's hope that we don't end up with such cases. But in most cases, if we have sum of squares, likeliness of it being positive definite is actually very high, right? So we're going to use that idea. So how can we find V of x to be sum of squares, also satisfying V prime of x times f of x is also negative definite, right? Now, if fx happens to be a polynomial, you know, some kind of x1 squared times x2 cube and so on, and you know, the vector f of contains only polynomials, you know, expressions, bunch of expressions like x1 power m, x2 power n, x3 power k, and so on and so forth. You have summation, linear combination of such expressions. Then, you know, perhaps we can try to put that in a programming format and then solve it, right? So the idea of sum of squares involves searching for Lyapunov functions candidates that are of the form sum of squares, right? And also we can write this V prime of x, right? So anyway, we'll proceed with this v of x. So instead of searching in general, we can actually look for v of x in the form of g transpose of x times p times g of x, where g itself is basically has bunch of monomials. I mean, expressions like x1, x2, x3, then perhaps x1, x2, x2, x3, x3, x1, and so on, and of every order. And of course, I don't mean that basically it's going to be an infinite vector or something like that, but we have to put some restriction. Perhaps g of x will have at most degree some n or something like that, m or something like that, right? So we'll go take all the expressions that have total degree, less than or equal to n or something like that, right? It will be some finite vector of bunch of monomials, and we'll pick p to be symmetric and non-negative definite, right? So that g transpose of x p times g of x will most probably positive definite. In fact, it will be positive definite in our definition if certain things are true about certain elements in that p. Okay, so we will search for now p rather than anything else, right? Now, and v prime of f x times f of x, we have this g of x times p times g of x, right? Where we can take derivative. We have an expression for that in terms of p, and f is coming from a polynomial. We'll have some other complicated m times this g of x. So when we take all those things, I want to put this argument a little bit carefully. So g of x contains all possible expressions like x1, x12, x1, x2, x2 square, and things like that up to a certain degree. And let's hope that f also has the same feature, or it has all the expressions up to a certain degree. So which means you can write f of x as a product of some matrix times this g of x. Okay, so hopefully that's relatively straightforward. Now, v prime of x is derivative of this, so you can only go lesser in degree when we take the derivative. So basically, you will end up with basic, a product also of the form g of x times q times g of x, right? I'm not going to details to understand, but I think intuitively it makes perfect sense, right? And we want this q to be negative definite. Okay, q, what is q? Q comes from your matrix coming from f as well as p. So what is the problem that therefore boils down to? We are looking for p, okay, such that both p is positive definite and q is positive definite. Okay, that's it. I mean, g of x is basically in some sense constant. I mean, we know exactly what it is, right? We are not really we don't have a variable there. We're not looking for x particular point or something like that. So g of x is a fixed quantity, so to speak. A p is what we are looking for, where p has to be non-negative definite, and q, which depends on p and other numbers, fixed numbers coming from f, has to satisfy also q less than or equal to 0, right? If both p and q satisfies both p positive non-negative definite, and then q p has to be non-negative definite and q has to be non-positive definite. If both are satisfied and we can find such a p, then we have a Lyapunov function, so to speak, right? So the nice thing about the method of sum of squares is basically this problem can be solved using linear matrix inequalities are exactly the same, except this g of x we are talking about is bunch of x1, x2, x3, x4, and so on and so forth, right? We are looking for matrix inequalities satisfying, which is equivalent to looking at quadratic forms. X transpose, what is p positive definite? X transpose p x is positive for all x. So same logic applies, and then basically you can use the general semi-definite programming tools to solve this particular problem. And fortunately, the person, Pablo Parello, who worked on this particular idea as part of his thesis back in 2000, is a controls person. So therefore, the methods that he developed actually has methods to find directly Lyapunov functions given an f(x), right? So please note that this is a typo. This is actually p greater than or equal to 0 and q less than or equal to 0, right? So we don't have to work very hard for this in terms of finding solutions, because there is a MATLAB programs that Caltech website has. Currently it's still not part of your MATLAB package, but hopefully eventually it will be. But if you're adventurous enough, one can actually go to this particular toolbox given by Caltech, and then you can download that and solve these problems, right? So this is a and then there are a couple of references that I provide in terms of where you can find tutorials. All I think are probably coming from Caltech. The original reference by Perillo is his thesis. The second one is more on these are the persons actually who worked on the toolbox, I think, and then basically they provided a tutorial on sum of squares techniques for systems analysis, specifically for Lyapunov functions and things like that. And the toolbox itself can be found at this particular URL. And essentially what the problem boils down to is you take this f of x, you write it in a particular manner, the program syntax requires you to write in a certain manner, and then actually after that it's looking for p and q is already embedded in the toolbox as a program, and then just basically ask for Lyapunov function, and it provides the Lyapunov function. So it's that simple from an application perspective. Okay, so sum of squares is one of the most generic way, and then computational way. I mean, all the other things require you to guess, and basically for small problems we can actually try to find. That's still a very powerful techniques, because like I said, it's still an art at this particular time. So one has to practice enough because you have too many nonlinearities and things like that. For those systems, one has to do this pen and paper kind of approach. But if you have polynomial systems and things like that, then this is a fantastic approach. And more importantly, if you have a non-polynomial system, one can still approximate with polynomial, and then actually you can get the extension of linearization through this sum of squares approach, and that provides much better domains of attraction rather than small domains of attraction coming from linear. And we also know that in many cases the standard linearization may not give you anything, but one can actually get polynomial perhaps what do you call Lyapunov functions that are not linear but more higher polynomials. One can actually hope for better results, right? So if we can actually approximate f of x with polynomials, if it's smooth enough that we can do that, we can get better local results than linearization approach. So this is a very powerful method which we won't be going through some of the details, but certainly quite useful method for you to look. Okay, so that brings us to an end of the second lecture of this week, which is basically construction of Lyapunov functions. In the next lecture, we will close the first part of the series, essentially looking at bunch of disparate small problems. Each one of them are extensions to what I spoke, or special cases in certain cases, and maybe 4 or 5 of those things to understand how some of the things that we haven't covered in this can be actually dealt with. Okay, thank you.